Thank you very much for the invitation and opportunity to talk at this event. So can colleagues hear me okay?
Yeah, sure. Perfect.
Okay, excellent. So my name is Yang Gao. I'm a professor of space autonomous systems at the University of Surrey. I had the space technology for autonomous and robotic system laboratory, or STAR Lab in short. I've been a space roboticist for nearly 20 years. It's an opportunity today for me to share some of our findings and latest developments in relation to AI robotics for our space exploration and exploitation missions. Of course, not all the work I will be presenting have been done for asteroid mining missions because there are a limited number of them. But of course, it is upcoming a mission, upcoming adventure for the space community. There are a lot to look forward to. But I hope what I'm going to present today is going to help stimulate some discussions or identify synergies between some of the existing space exploration missions and this more futuristic mission concept. I'm going to talk about various work we've done in AI robotics in two principal space mission scenario. One is looking at orbital scenario, and this are principally looking at the missions that look at space debris removal or clean space. On orbit assembly, deployment, satellite servicing, constellation formation flying, etc. And this are looking at, for example, different type of targets in orbit that we want to use robotic systems on the spacecraft to interact with, and this are typically looking at either cooperative targets or non-cooperative targets. I think for asteroid mining, depends on different stages of the mission, of the investigation. You could be principally looking at non-cooperative target, but also potentially cooperative target in some other cases. And from the engineering point of view, the challenges comes from two type of hosting forms for the robotic system. It can either be deployed from what we call a pseudo-fixed platform, such as the space stations, or extremely large spacecraft compared to the robotic element, or free-flying platforms where there is a reasonable ratio between the robotic element and the base spacecraft. And we know as we're speaking, there are already missions or applications that demand very advanced AI robotic capabilities, and particularly in the time frame of 2025 to 2035, we envisage a huge number of missions that would be launched that carry this kind of robotic systems. The first example I'd like to give, looks at visual sensing for formation flying spacecraft, and this is a mission, a European Space Agency led mission called Propos 3 that look at demonstrating precise or precision formation flying between two spacecraft to study the solar corona. And the work we have involved in supporting the industry is to develop the laser-based fine lateral and longitudinal system for relative attitude determination between the two spacecraft. And here the challenge is trying to achieve a high accuracy up to 300 micron for distance up to 200 50 meters between the two spacecraft. And it's quite challenging, particularly for the lateral measurement, where you have to track the beam motions at a very fine accuracy and also the precision. As you can see from the pictures here, where a small motion, I think, is going to, a small difference between the pixels is going to generate huge discrepancies in the measurement. So our technique have introduced machine learning in order to help with some of the calibration work, and for people who are interested can pick up the publications that offers more technical details, which I don't have time to go through given the time limitation today. Another example is looking at orbital navigation, again through vision processing. Here, the idea is trying to achieve low computational relative navigation for spacecraft, in this case for in-orbit servicing assembly. And here, the hidden narrative is you're potentially looking at a copper target here in orbit where you're trying to navigate and potentially do run-to-run docking with. So here, in order to reduce the computational load, which we know is a constraint for space systems, we adopt approach that is quite novel, which is only using monocular vision here for post-estimation, so that it is very low in demand of computation and can work very high speed on the flight. And we also adopted a convolutional neural network based approach, allowing deep learning, so we can train based on a pre-existing data for better accuracy and adaptability. And this was also validated using some of the in-house developed software that is available for both academic and industry use for benchmarking and validation. And the film playing here is to compare the data set that we have created using our simulator with the real world data set, which you can see the realism of what the simulator can generate and help us validate some of the techniques. This slide is showing a hardware in the loop testing of the technique, just to help develop further the TRL. So in here, you can see the arm on the left in the film is acting as a servicing arm on your mobile spacecraft, while on the right-hand side, which is a target object in orbit, in this case, which is a mirror segment for in-orbit assembly missions. And that's basically carried by the second robotic arm in the lab setting. So here we assume the rendezvous has been achieved already, so there's only relative motion between the end-effector of the two arms, so there's no relative motion on the base. So where you can see that the camera view, it's on the left top corner there. You can see that because of using the machine learning technique, even during the time where there is a loss of sight of the target on the camera of the servicing arm, the servicing spacecraft can still successfully perform the relative navigation and docking with the target objects. I'm just going to fast track this because this is just a repetition. Okay, so again, this is looking at a cover target scenario, but of course, another interest is how to perform this kind of navigation and docking with non-covered targets. So in this case, we developed technique using visual based navigation for manipulation grasping. And this could be applied to the active debris removal scenario. And I think this is probably a more close application to the future asteroid mining situation. Here, the technique again is looking at low computational approach so that we can operate comfortably and confidently this techniques on board the spacecraft. And instead of looking at a completely 3D mapping of the target object in space, we look at just using the sparse point clouds for the sensing. And here, with the introduction of machine learning, we can also work with noise and uncertainty. So it's all very resilient in the actual operation. There's also introduction of verification validation of the GNC algorithm, which is quite important for some of the robotic or autonomous decision making in real time. So the film that's playing on this slide, on the top, you can see a simulation, computer simulation results with the servicing arm and with a gripper as an effector is approaching a target object in space. In this case, it's a nozzle of the span motor, which is one of the mostly populated space debris right now in Earth's orbit. Well, on the bottom here is basically the hardware demonstration of the same operation. So you can see the relative navigation works very well in the last proximity phase. And the grasping is also very successful with an unknown target where we can identify the most appropriate surface to grasp completely autonomously, and also the final stage of the retrieval, which is also a key step. So besides the orbital scenario, there's of course the interplanetary surface scenario where AI robotics is going to play a significant role in future missions, such as asteroid landing or mining. Here looking over the horizon, there are a number of sample return missions being planned, such as the Chinese Chang'e 6 mission following the success of Chang'e 5, and also the joint venture between ESA and NASA on Mars sample return. These are missions where really require some prophet rovers to explore unstructured terrains and collecting surface and subsurface samples. Beyond 2030s, we believe there will also be missions looking at manufacturing, assembly, in-situ resource utilization applications. One of the initiatives, the ESA's Moon Village. Of course, there's this recently announced joint venture between China and Russia in terms of establishing international lunar research station. There are the various kind of commercial exploitation initiatives, of course, including small bodies like asteroids. In terms of robotics requirements, in this category, we believe there's a demand for heterogeneous robotic elements, building infrastructures. There's also a demand for creating human/robot ecosystems around, for example, the source pole of the moon, where there is a desire to set up a human permanent habitation there. In terms of examples of existing development, we have contributed to one example looking at visual guided navigation solution for high accuracy robotic arm placement for sample collection or sample acquisition. For example, this can apply to Mars sample return mission, or I think you can potentially look at implementing this for asteroids as well. Here, the technique look at using visual saliencies to address robust feature tracking on homogeneous scenes on planetary surface, such as you have a rocky terrain, or some of the images I think being shown by previous speakers, I think speaks a lot about the challenges, how homogeneous some of this environment interplanetary extraterrestrial services are. They look rather homogeneous. It can be very stressful to use visual cues to guide the robotic systems. When you are on a further view where you have the boundaries, or for example, for rocks and textures, that's still fine. But when you start to get zoomed into or get closer to certain rocks, and you can appreciate the difficulties of identifying features and tracking them reliably. So you need to have artificial intelligence to help you perform a very good trade-off between the stress on the computational load and detection accuracy and precision. So this kind of technique are really very important to guide robotic tools to best place in actually target area, for example, for your sample collection. Another project example we have done for this kind of exploratory missions is to do with Chang'e 3. So that was the collaboration between our research lab and Chinese Academy of Sciences, where we have helped to provide some deep analytical studies on the data coming from the Chang'e 3 rover. So you can see from the picture here on the left, top left, which is a high resolution surface terrain image of the rover, looking back the track of the rover. And of course, the rover has encountered some mechanical difficulties after traverse about 150 meters. So it couldn't carry on further, but it's very useful. It provided huge amount of high resolution images of the terrain around the Chang'e 3 landing sites. So we actually come up with an idea that combined the shape from shading technique with terra mechanics that allows us to derive the soil stiffness or strength through our analysis of the Chang'e landing site. And we managed to apply the same technique using the data from the Apollo 15 and Luna 17 and produce a comparison across the 3 landing sites, which gave quite interesting findings of the soil strength at the shallow depths of this landing sites, which I think also being picked up by the Chang'e team to help inform them for future missions. Similarly, we've been using visual data processing techniques for surface navigation operation for also European rovers. So there is a ExoMars 2022 rover, I think it's going to be launched this year, or if it got affected then by COVID again, then we're probably looking at the actual operation of the rover next year. And here we're collaborating with our European consortium, looking at autonomous data pipelines for processing the panoramic camera image. Here, this combines processing of the 3D point clouds with data fusion, with other informations coming from the mission and the satellites, and produce a GIS system that can be supporting both the scientific team in terms of object detection, recognition, as well as the actual engineering operation of the rover. Moving to the next examples of technology, here we look at how to enhance the surface mobility of the small robotic systems for future exploration or exploitation missions. Here is a technique that was inspired by biological system, which through a design of active suspension to allow a crawling and climbing behaviors for micro rover design. So this could be very small robotic surface vehicle, something around 10 kilo in terms of mass. So on the film here, I'm showing how the mechanism with only two actuation systems allowing crawling behaviors on the surface to, for example, for entrapment retrieval. So on the top here, you can see how the actual mechanism works in principle. And then on the below here is actual physical testing of the technique. As you can see, the rover was first stuck in loose sand, and then using the crawling behavior, it can actually come off the sand, the entrapment on itself. And similarly, within the exact same mechanism, I'm showing the climbing behaviors, and this, of course, helped to negotiate with rocky terrains. And similarly, below the simulation, I'm showing the actual physical testing, as you can see, with a small rover of about 10 kilo or 10 to 20 kilo, the rover can negotiate an obstacle which is a height of 1.5 to even 2 times the height of the diameter of the rover well, which is quite extraordinary thing to achieve. Just going on about sampling, because quite a number of speakers, I think in conferences talk about asteroid mining, talk about sampling and drilling, because that's quite critical. Here we have developed technologies for subsurface sampling and drilling, which particularly designed to work in microgravity environments. So this was actually a design also inspired by biological system. It utilized a very novel drilling technique called dual-reciprocation drilling, which is very different from rotary or percussive drilling, which are very commonly used. And in this technology, which is called WASP drill in short, you can see from the simulation film here on the top left, which demonstrates the behavior of the drill bit with the regulus and granular particle surrounding it. As you can see, the penetration is achieved by the traction between the drill bit and the regulus. And on the right-hand side is the actual testing in the laboratory, where we use a Martian simulants for this particular experiment. Similarly, sampling is deemed important in some of the missions. So we incorporated the sampling mechanism into the WASP drill technology, as you can see from the sort of the bottom animation on the left hand side. which shows the inner mechanisms, how that is achieved. And then similarly, we have the film to the left, where it shows the actual experiment, and we color the sand so that we can see we can analyze the particle movement afterwards more easily. I don't know why it's not playing, but yeah, but that gives you your idea. Another, probably one of my last technical slides is to do with the robot-soil interaction. I think particularly our last speaker talked about some of the behaviors of the particle in asteroids. There are a lot of unknowns, obviously, in places we have to go for the first time. So that shows sometimes how important it is to perform on-ground simulations, go through various possibilities to allow us develop our engineering solutions as reliable as possible. So here we have techniques that help us to prepare the simulants for extraterrestrial soil and regulars, and particularly we've been focusing on Mars and the Moon because they've been popular targets, but we're very happy to extend that into the asteroids as in the future. So, but the same sort of kind of knowledge of hosting this kind of capability, I think applies, across the board, and they're quite generic. So I'm also trying to stress the importance of some of the numerical modeling capabilities that we have here. So for example, on the left, you can see an EBM simulation of how the soil would interact with the wheels of the rover of the service vehicle. And also similar on the right-hand side, you can see the particle interaction with the actual drilling or sampling tools. I want to just spend very quickly a few seconds talk about the future, looking into the future, which really are the key gaps in the robotic and AI development to help enable sustainable in-space operation. I think in the long term, what we're really looking at as a community is to achieve long-lived and robust solutions, both on the mobility front, on the autonomy front, for future generation of spacecraft. I'm sure this applies to asteroid mining as well. So in the immediate term, there are a number of key challenges we have to try to achieve or address in order to achieve more sustainable designs for future robotic spacecraft. That includes things like low computational high accuracy mapping and perception techniques, energy optimized locomotion solutions in terms of mechanisms, in terms of all control, everything we do computationally on board the spacecraft, should it be data analysis, data processing, or decision making, it has to be resource aware. We also need to look at hardware and software reconfiguration and self-verification so that what we develop are trusted systems. This is just example of this kind of, my vision of the AI robotics moving into the future. We have to move from the weak AI to strong AI. One example is reconfigurable autonomy, technology we've been developing for the past few years. And here is just is a film playing here to show one of the navigation system that we adopted, reconfigurability of the software in real time of the operation of the mission, where you can switch between different algorithms for the navigation solution. Just a bit of a PR, there is a new book that has been recently published, edited by myself, looking at some of the latest very latest development in AI robotics, which is cover very wide range of topics from navigation, sensing mechanisms to astronaut robot interaction, verification, and cybersecurity of this systems or robotic space systems. So if people are interested. So with that, I thank you so much for your time and listening to this talk.